Okay, it is good to recall some key points from the previous lecture. As you recall, I discussed eigenvalues and eigenvectors of a matrix. Before that, I told you some points. The non-homogeneous system of linear equations, Ax equal to b. If b is non-zero, it is non-homogeneous. And if b equal to 0 means Ax equal to 0. Then it is called homogeneous system of linear equations. For homogeneous system, x equal to 0 is always a solution. This is called trivial solution. And you can see clearly x equal to 0 satisfies it. If you put x equal to 0 in Ax, you are getting 0. Remember that it is a null matrix. Okay. So x equal to 0 always satisfies the homogeneous system. It is trivial solution. What about other solutions? Depends on the determinant of A. If determinant of A is non-zero, then you have trivial solution x equal to 0. And if determinant A is 0, then this system, this homogeneous system has infinitely many solutions. Do you recall all this? Okay, all right. Now, understand this point, why you get infinitely many solutions when determinant is 0 and why you get only trivial solution when determinant is non-zero. You see, when determinant is non-zero, A inverse exists. Do you recall this result from your 12th class? When determinant is non-zero, A inverse exists. What is A inverse? Adjoint A upon determinant A. So if determinant A non-zero, that guarantees that A inverse exists. Now if A inverse exists, look at the system. If I pre-multiply by A inverse on both sides, what do I get? This expression A inverse into A gives me unit matrix, right hand side 0. This means x equal to 0 only. So if A inverse exists, then you get always the trivial solution from this for this homogeneous system. Is it correct? So
Yes, sir.
that's why we use it. All
Okay, sir.
right. Please answer your things in the chat box. No need to speak. Okay. Next point. What are eigenvalues of a matrix? If A is n cross n matrix, then eigenvalues are given by this equation. Determinant A minus lambda in equal to 0. This is an equation in lambda of nth degree. You will get n values of lambda. Those are eigenvalues of A. Lambda is eigenvalue. And how many values of lambda you will get? N values from it. Next, eigenvector corresponding to some value of lambda. How do you get eigenvector? You solve this matrix equation. In fact, you solve this homogeneous system. From the solution of this homogeneous system, you get the value of x. That is your eigenvector. After that, I told you if it is triangular matrix, means either above diagonal elements are 0 or below diagonal elements are 0. What are eigenvalues for such a matrix? All the diagonal elements. Okay. So these are the points we discussed in the previous lecture. Now see this matrix 1 0 0 0 1 0 0 0 1. So what is the characteristic equation for this? Means this equation 1 minus lambda 0, 0, 0, 1 minus lambda, 0, 0, 0, 1 minus lambda. If you solve this determinant, simply the product of diagonal entries, that is 1 minus lambda power 3. 1 minus lambda power 3 equal to 0. This gives you 3 repeated values, 1, 1, 1. Now corresponding to 1, how to get the eigenvalues? Sorry, eigenvectors. You will write this equation, this matrix equation, A minus lambda I3 x equal to 0. But this time lambda is 1 and A is I3. A itself is unit matrix. This is your A. So you get I3 minus I3. Lambda is 1. Means you get this kind of situation, 0, 0, 0, 0, 0, 0, 0, 0, 0. Otherwise also you can understand from here, if I put lambda equal to 1, diagonal entries become 0. So you get a null matrix. Here are the entries of capital X, right hand side is 0, 0, 0. Now you need to solve the system. You are not getting any equation. If you consider first row, first this column, then you are getting 0 equal to 0. What does it mean? For all three the same thing. You are not getting any equations in x1, x2, x3. It means x1, x2, x3 all are arbitrary. So assume x1 equal to some arbitrary constant, x2 equal to some arbitrary constant, and x3 equal to also some arbitrary constant. So what is your eigenvector corresponding to lambda equal to 1? x2, x3, x1, x2, x3, but these are all arbitrary. You can write ABC. Then you can break it into 3, 1, 0, 0, then B times 0, 1, 0, plus C times 0, 0, 1. So this whole linear combination is eigenvector, and you can say you are getting 3 linearly independent eigenvectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Interestingly, these are, you can say, row vectors or column vectors of the unit matrix. Okay, so these are 3 linearly independent eigenvectors. Linearly independent, I tell you again what is the meaning of linearly independent eigenvectors. Independent eigenvectors or simply vectors. If there are two vectors, it is very easy to say x1 and x2 are linearly independent if these are not multiple of each other for any constant. If these are not multiple of each other, then these are linearly independent. It is same as saying that x1 minus for any constant a, x2 is non-zero. Isn't it? They are not multiple of each other. If these are multiple of each other, then what to say? These are linearly dependent through this linear relation. That's why the word linearly dependent. Through a linear relation, these are connected. Now let me tell you the general definition. Suppose there are n vectors, x1 to xn. When you say these are linearly independent, if their linear combination means multiply these vectors by numbers a1 to an, put this combination equal to 0 vector. Now from this you have a linear system in x1 to xn. Okay, you have a linear system. Okay, write it here again. x1 to xn are linearly independent if a1 x1 plus and so on an xn equal to 0 implies all these constants are 0. You see, if you put all these zero, naturally this relation is satisfied. But if this relation means this left hand side is zero for some non-zero AI, for some constant non-zero, then these are linearly dependent. So remember this relation. This is the perfect definition for linearly independent vectors. Means the linear combination of the vectors is zero only when all the scalars are zero. All these numbers are zero. In that case, the vectors are linearly independent. Even if you get any of these scalars non-zero, then these are dependent. For two vectors, very easy to see directly. If they are multiple of each other, then these are linearly dependent, otherwise independent. Got it? The idea of linearly independent vectors. Here you can see that this vector 1, 0, 0 and 0, 1, 0, these are not multiple of each other. Whatever constant you multiply here, this vector and this vector cannot be multiple of each other. Am I right? That's why these are independent. Okay. Likewise, these two are independent. And if you put this combination of the three vectors equal to zero, this is perfectly the combination. You see, ABC will be zero only. All three zero. That's why these are linearly independent. So hope you understand this idea. Okay. Now, for unit matrix, you are seeing that lambda equal to 1 is repeating 3 times. And you are getting three linearly independent eigenvectors. Now consider this matrix and without calculating anything, tell me what are its eigenvalues and what are the eigenvectors without doing any calculation. Eigenvalues are 0, 0, 0, correct, because it is upper triangular matrix, so diagonal entries, fine. Eigenvectors corresponding to lambda equal to 0, what are eigenvectors? You know, if you solve a minus lambda I3 equal x equal to 0, lambda is 0 here, so you will write simply a. A means 0, 1, 0, 0, 0, 1, 0, 0, 0, x1, x2, x3 equal to 0, 0, 0. What equations you get from the system? Because its non-trivial solution gives you eigenvector. What you get? You are getting from the first row, you are getting x2 equal to 0. Because if you multiply this with this, you get x2 equal to 0. Likewise, second row multiplication with x1, x2, x3 gives x3 equal to 0. What does it mean? These two are fixed. X1 is arbitrary. Let us assume it A. So what is eigenvector in this case? Your eigenvector x1, x2, x3. x2 and x3 are fixed to 0. This is A. x1 is A. So any non-zero multiple of 1, 0, 0 is eigenvector of this. Correct? Any non-zero multiple of 1, 0, 0 is eigenvector of this. Interesting. Lambda equal to 0 is repeating 3 times. We call it algebraic multiplicity. Algebraic multiplicity. A. The number of times some eigenvalue repeats, it is called algebraic multiplicity. So lambda for lambda equal to 0, algebraic multiplicity is 3, but you are getting only one eigenvector. In case of unit vector, algebraic multiplicity of 1 is 3. But in this case, you are getting 3 eigenvectors. These 1, 0, 0, 0, 1, 0 and 0, 0, 1. Okay. Now consider this matrix. This will give you further information. 0, 1, 0, 0, 0, 0, 0, 0, 0. What are eigenvalues? Again all 0. And eigenvector, you need not to calculate this time. You can think directly. This time x2 is fixed. X2 is fixed to 0. It means x1 and x3 will stay arbitrary. Am I right? X1 and x3 will be arbitrary in this case. So what is your eigenvector in this case? Linear combination of, or let me first write in terms of AB, A0B. How can you write it? A times 1, 0, 0 plus B times 0, 0, 1. Is it correct? Okay, so it means this time you are getting two independent eigenvectors, 1, 0, 0, 0, 0, 1. Same eigenvalues, same algebraic multiplicity, but two eigenvectors. In the previous case, you got only one eigenvector. In case of unit matrix, again, the algebraic multiplicity is 3, but you are getting three eigenvectors. It means it depends on the matrix. Corresponding to a repeated eigenvalue, you can get less number of eigenvectors also. Independent eigenvectors, I am telling. Okay, you can get the same number of eigenvectors, or you may get less number of eigenvectors. It depends on the matrix. Is this point clear? For a repeated eigenvalue, suppose some eigenvalue is repeating 3 times. For example, in case of unit matrix, you were getting 3 independent eigenvectors. But in this example, you are getting only one independent eigenvector. In the next example, again, there are 3 eigenvalues, but you are getting, means eigenvalue is repeating 3 times, but you are getting 2 independent eigenvectors. So this point should be clear. Eigenvalue may repeat any number of times, but it is not necessary that you will get that number of independent eigenvectors. It may be same or it may be less also. Clear? From these examples? Okay, good. Now, let's go to the next topic. Rather, it is again related to the eigenvalues, properties of eigenvalues. There are some useful properties that you can prove easily. First property is sum of eigenvalues of a matrix. Sum of eigenvalues is equal to trace of A. Do you understand the meaning of trace? Trace of A means sum of diagonal elements of A. Diagonal elements of A. Okay. Let me write one more property here. We will prove both the properties together for a 2 cross 2 matrix. Product of eigenvalues. Product of eigenvalues is equal to determinant of the matrix. Let's prove for a 2 cross 2 matrix. You can prove it in general also. I will see if I will put general proof in the lecture notes. You can see there. Let's do it for a 2 cross 2 matrix. Consider a 2 cross 2 matrix A11, A12, A21, A22. Okay, how to get its eigenvalues? Determinant of A minus lambda I equal to 0. I can also write it in this format. Lambda I minus A equal to 0. Both are same or not? Both are same or different? Both are same. Because right hand side is 0, you can balance minus, no problem. Okay, write it in matrix form, means in determinant form, full determinant form. What do you get? Lambda minus a11 minus a12, then minus a21 and lambda minus a22 equal to 0. Solve this determinant. What do you get? You get lambda square minus a11 plus a22 times lambda plus a11 a22 minus a21 a12. Check it whether I've written correctly. Is it correct? Yes. Now if lambda 1, lambda 2 are eigenvalues of A, this expression is a second degree polynomial in lambda, right? So this expression lambda I minus A can be written as lambda minus lambda 1 into lambda minus lambda 2. Naturally, lambda 1 and lambda 2 are factors of this because these are roots of the characteristic equation. So what do you get from here? Lambda square minus lambda 1 plus lambda 2 times lambda plus lambda 1 lambda 2. This is another characteristic equation in terms of lambda 1 lambda 2. This you have solved from the given matrix. Compare the two. See what do you get. What is lambda 1 plus lambda 2? A11 plus A22. Is it trace of A or not? Yes. Trace of A means sum of these diagonal elements. You are seeing it. And what is product of lambda 1 lambda 2 from here? See what is it? Is it determinant A or not? Yes. So you see you are easily able to verify both these properties, that sum of eigenvalues is trace of A and product of eigenvalues is determinant of A. But this gives us further information, so some very useful information. What? If determinant A is 0, suppose, then at least one of the eigenvalues would be 0. Am I right? If determinant A is 0, then at least one eigenvalue should be 0, must be 0. Yes, because this can be 0 only when one of the eigenvalues is 0 or more than one. So it tells you that if you see eigenvalue, some eigenvalue of a matrix equal to 0, naturally determinant of that matrix would be 0 and vice versa. Clear? Means without doing anything, if you find determinant of a matrix and you are saying it is 0, then you can certainly guarantee that one eigenvalue at least is 0 from this. All right? Okay, good. Now let's see third property. If lambda is eigenvalue of A, this eigenvalue is a single word, okay? There is no gap. Eigenvalue, complete word. If lambda is eigenvalue of A, then lambda power m is eigenvalue of A power m. Of A power m. Let's see. Lambda is eigenvalue of A. That means Ax equal to lambda x, correct? By definition. Lambda is eigenvalue of A, so X should be lambda X for some non-zero X. If I multiply both sides by A, what happens? Lambda is a number, X is a matrix, so you can write AX, lambda times AX. So it is A square X equal to this AX can again be replaced by lambda X, correct? This AX can be replaced by lambda X. So you get lambda square X, right? But this expression shows you something. Can I write from this expression that lambda square is eigenvalue of A square? Is it right? Yes. In place of lambda, you are saying lambda square. In place of A, you are saying A square. It's exactly the definition of eigenvalue. So now you understand, if I again it multiply by A, then it would be A square I can replace by lambda square X, and you can continue. So in general, you can say lambda power m is eigenvalue of A power m, right? Okay. Next property, if lambda is eigenvalue of A again, then 1 over lambda is eigenvalue of A inverse. A inverse. Naturally, lambda should be non-zero because A inverse can exist only when determinant is non-zero. You understand that point. Here, lambda is non-zero. It's understood. If lambda is eigenvalue of A, then 1 over lambda is eigenvalue of A inverse. How can you show this? Very easy. Lambda is eigenvalue of A. That means there exists some non-zero vector x such that Ax equal to lambda x by definition. Because A inverse exists, let's pre-multiply by A inverse on both sides. See what do we get. Remember that lambda is a number. A inverse gets multiplied with capital X. Alright, what is A inverse A? Unit matrix. Lambda times A inverse X. Let's divide both sides by lambda. Ix is X, naturally. Lambda times A inverse X. Now divide both sides by 1 over lambda. What do you get? 1 over lambda times X equal to A inverse X. Now see this carefully, this expression. A inverse X equal to 1 over lambda times X. In place of A, you are seeing A inverse. In place of lambda, you are seeing 1 over lambda. It is exactly the definition of eigenvalue. So from this, what can you say? 1 over lambda is eigenvalue of A inverse. Is it right? Yes, good. So now you understand it. It's just a manipulation from the definition of eigenvalue. You can prove some more properties also. From maybe some problems are given in the textbook. You can see there. But you understood all these four properties, right? That I have shown you here. Okay, very good. After the properties, let's move to the next topic. That is similar matrices. Similar matrices. You will see some interesting things here. Suppose A is a given matrix of order n cross n. It is said to be similar to a matrix B is similar to B if there exists a non-singular matrix. Non-singular, you understand? With determinant non-zero means a inverse of the matrix is guaranteed. Non-singular matrix P such that P inverse A P equal to B. This is the definition of similar matrices. See it again. A matrix A is similar to B if there exists a non-singular matrix P such that P inverse AP equal to B. If you can establish this kind of relationship for some by finding some matrix P, then A is similar to B. Further, one more definition. If B equal to some diagonal matrix, if I'm adding one more definition to it, if B equal to D is some diagonal matrix, then A is a diagonalizable matrix. We say that A is a diagonalizable matrix. So note down the definition of diagonalizable matrix. A is diagonalizable if you can find a non-singular matrix P such that P inverse AP equal to D, where D is a diagonal matrix. If this happens, then, or you can say A is similar to some diagonal matrix. It's the same thing, similar to D. If A is similar to some diagonal matrix, then A is called diagonalizable matrix. Okay. So you understand the definition of similar matrices and diagonalizable matrix. Now I tell you a very important result. You should see it carefully. How to find this capital P, whether it always exists or what is the procedure to find it. See what I'm writing. Suppose I will connect this thing with the eigenvalues and eigenvectors very beautifully. You will see that there is some interesting result that connects this similarity thing with eigenvalues and eigenvectors. Suppose there exist n linearly independent. This linearly independent is important here. Suppose there exist n linearly independent eigenvectors of the matrix A. Then let me name the eigenvectors x1 to xn. Then A is diagonalizable, number one. Then A is diagonalizable. With P equal to x1, x2, P is a matrix with column entries x1 to xn. Means P inverse AP is a diagonal matrix. And interestingly, that diagonal matrix at diagonal places exactly carries the eigenvalues of the matrix A. I will prove it, don't worry. Just see the result. I repeat this result again, what I'm trying to tell you. Suppose there exist n linearly independent eigenvectors of A with eigenvalues lambda 1, lambda 2, lambda n and eigenvectors x1 to xn. Suppose. Then A is diagonalizable and P, how to write P? Write the column vectors of P as the eigenvectors x1 to xn. After that, we can prove that P inverse AP is nothing but this diagonal matrix. And most interesting thing is that in this diagonalization, the diagonal matrix exactly carries the eigenvalues of A. Let's prove it. Proof would be interesting. It's easy, just a one-line proof, we can do it. Let's start with A times P. What is P? X1 to xn. You have constructed P using the eigenvectors of A. So it is AX1 to AXN. Okay, this I can write as x1 to xn. No, AX1 can be replaced by lambda 1 x1 and so on. AXN can be replaced by lambda and xn. Why? Because you are saying that lambda 1 is eigenvalue, x1 is the corresponding eigenvector. So AX1 should be lambda x1, lambda 1 x1. Likewise, AX2 should be lambda 2 x2 and so on. Now you understand why I have done these replacements here. Okay. This can be written as x1 to xn, the diagonal matrix x lambda 1, 0 and so on, 0, 0, lambda 2 and so on, 0, 0, 0 and so on, lambda. Okay, check it. If I multiply these with this matrix, I will get the previous matrix. This is your P. Now you are solving A times P. A times P equal to P times this diagonal matrix. So if I pre-multiply by P inverse on both sides, what do I get? This matrix. Lambda 1, 0 and so on, 0. 0, lambda 2 and so on, 0, 0, 0. A diagonal matrix with diagonal entries exactly the eigenvalues of the matrix. Is this clear? Okay, proof is simple. You can focus on the steps of the proof later, but the result is very important. You should see this result again. If a matrix has n linearly independent eigenvectors, say x1 to xn, and the corresponding eigenvalues are lambda 1 to lambda n, then A is always diagonalizable. It means what is the condition for diagonalization? The matrix should have n linearly independent eigenvectors. N means we are considering the order of the matrix n cross n. Okay. So if the matrix A has n linearly independent eigenvectors, it is always diagonalizable. And how to diagonalize it? Construct the matrix P using the eigenvectors as columns. If you solve this thing P inverse AP, you get a diagonal matrix, and not only that, in this diagonal matrix, the diagonal entries are eigenvalues of A. This is another beautiful thing. So you see how similar matrices are connected. Once the matrix is diagonalizable, all things are interrelated. There is some interplay between the things. You understood this concept? Shall I move further? Okay, good. Now, our job is to search when we can get n linearly independent eigenvectors, because if the matrix has n linearly independent eigenvectors, it is diagonalizable, and we know the answer of diagonalized matrix also. Just we have to write a diagonal matrix with diagonal entries as eigenvalues, and we know capital P also. Now, if a matrix of order n cross n is given to you, what can you say about linearly independent eigenvectors of this? That's the point now. Listen very carefully. If A has n different eigenvalues, means eigenvalues are not repeating. In this case, you will get, in this case, you will get n linearly independent eigenvectors. Then there exist n linearly independent eigenvectors. So no problem this time, in this case. Just find the eigenvalues of the matrix. If no eigenvalue is repeating, then you can directly say the matrix is diagonalizable. Clear? Corresponding to different eigenvalues, you will get independent eigenvectors. Problem appears when some eigenvalue is repeating, as I told you earlier. For example, in the unit matrix, eigenvalue is repeating 3 times. But in that case, you are getting 3 independent eigenvectors. So unit matrix is diagonalizable, and already you see unit matrix of order 3 cross 3 is already in diagonalized form. Is already in diagonalized form. What is capital P in this case? Itself. These are the eigenvectors. So for unit matrix, if I consider A equal to I3 and I solve P inverse AP, I will get I3 again because P is also I3, A is also I3. So in the end, you will get I3. Correct? So corresponding to a repeating eigenvalue, if you get the same number of independent eigenvectors, no problem, the matrix is diagonalizable. It is possible that you get less number of independent eigenvectors. You are not getting n independent eigenvectors, then the matrix is not diagonalizable. Is it clear? Then the matrix is not diagonalizable. For example, 0, 1, 0, 0, 0, 1. In this case, how many independent eigenvectors we get? 1, 2, or 3? Eigenvalue is repeating 3 times. What is eigenvector in this case? Only one eigenvector. So this matrix is not diagonalizable, okay? Because you are getting less number of independent eigenvectors. Next thing, if two matrices are similar, A and B are similar, then they have same eigenvalues. Why? Then they have same eigenvalues. Why? Can you understand this? If A and B are similar, there exists a matrix, non-singular matrix P, such that P inverse AP equal to B by definition. Using this result, can you prove that A and B both have same eigenvalues? Very easy. Suppose lambda is eigenvalue of A, or start with eigenvalue of B. You can start either side. If lambda is eigenvalue of B, then B minus determinant of B minus lambda I should be 0. Correct? This can be written as P inverse AP because B is P inverse AP. P inverse AP minus lambda equal to 0. You see the manipulation, it's very easy to prove. P inverse AP, this I can be written as P inverse P. If I multiply matrix with its inverse, I get INT matrix. This can be written as P inverse times A minus lambda I P. Correct? Yes. Now you know this result. If there are three matrices in multiplication, determinant can be written as determinant A into determinant B into determinant C. Use it. You can write P inverse determinant, determinant A minus lambda E, determinant P. Now club these two again. You get PP inverse determinant. That is unit matrix determinant. What is the determinant of unit matrix? 1. So you are left with only A minus lambda equal to 0. What does it mean? Lambda is eigenvalue of A because this is the characteristic equation of A. So A and B both have same eigenvalues. Likewise, you can prove that if X is eigenvector of B, then Px is eigenvector of A. This proof is given in the lecture notes. You can see from there. Okay, it's simple. So this is the connection between eigenvalues and eigenvectors of similar matrices. Final point for today's lecture. Then the lecture is finished. What is that? Suppose A is diagonalizable matrix. So P inverse AP is equal to a diagonal matrix. Am I right? By definition. If A is a diagonalizable matrix, then P inverse AP is a diagonal matrix. Okay. So if I square both sides, what happens? If I square both sides, D square, this side. But to the left side, something interesting happens. You can write it P inverse AP into P inverse AP. Solve it. See what do you get. PP inverse becomes unit matrix. That is gone after multiplication with other matrices. So you are left with P inverse A square P. Good. What does it mean? Let's pre-multiply by P and post-multiply by P inverse. So P D square P inverse. This step is correct. You understand this step? In this step, on both sides, I have pre-multiplied by P, post-multiplied by P inverse. What does it mean? If I further find A cube, same thing will happen. I can write P D2 P inverse. Even if I do A power 100, no problem. I can write P times D power 100 into P inverse. Now you'll be thinking, what is the advantage of doing all this? Advantage is that for a diagonal matrix, calculating powers is very easy. For example, I write this matrix 2, 0, 0, 5. If I ask you what is D square, you can immediately tell me it is 2 square, 0, 0, 5 square. If I ask you D power 100, no problem. You will say 2 power 100, 0, then 0 power 100. Calculating any power of diagonal matrix is very easy. Okay. But calculating any power of a given matrix is difficult because you have to multiply the matrix again and again. That is a lengthy process. So this result tells you that if you find P for the given matrix, means the matrix that diagonalizes A. If you find P, then use this result to get any power of A. Because once you find P, you know D also. D carries exactly the eigenvalues of A at the diagonal places. If you use P uh, as the matrix obtained from the eigenvectors of A. Correct? So you know P, you know D. Doing this calculation is very easy because finding D power 100 is very easy. Just you have to raise the powers, and after that just you need to multiply these two matrices. Job is done. So this kind of results are very important when you are writing a computer program, because computer needs less computations. One side you say, okay, I want A power 100 in my calculation. So computer has to multiply A 100 times. It will take a lot of time. Okay. But if you give this formula to the computer, it will do very easily. Because here the computation is D power 100 very fast. Then P and P inverse, after that it will multiply, no problem. So you understand the importance of these things. Okay. So now today you have learned very beautiful things, that how the eigenvalues and eigenvectors are connected in case of similar matrices and the meaning of diagonalization. Okay. So we will continue this discussion in the next lecture. So please be prepared with all these concepts.